Well, good morning, folks. Got to start it the same way we start the news every day. So for those who don't know, my name is Ben Davidson, and the YouTube channel is Suspicious Observers. If you Google it, you won't even get all the way through the word suspicious. It'll know what you're looking for. We do a space weather, earthquakes, and general science, space, electric universe news program every single day, and have done so every single day since 2011. And when I say every day, I don't mean we take weekends or holidays off. The Earth and the Sun aren't allowed to do that, so I'm not allowed to do it either. It got a little shaky the day my daughter was born, the day after my wedding, things like Christmas, my mama's birthday, but you know, some things are just important enough that you got to keep them going. Anyway, I want to thank Kong Pop for the shout out. Indeed, he does contribute, and we're very, very thankful that he does so. He mentioned Mitch Batros as well. Mitch Batros and Earth Changes Media have actually partnered with Suspicious Observers in the last month and a half, and so we have the very first space weather reporter now on board and looking into these same sorts of things, and I'm sort of getting his mind around to this as well. In fact, Mitch, over the years, has interviewed most of the members of the Thunderbolts project. But anyway, what I'm going to talk about today is going to quite rapidly enter your mind as something that is belonging right after Kong Pops. It's going to be a little more specific to the sun, and it's going to use a little bit more pictures, I guess we'll say. On the one side, you have the sun and its magnetic fields. On the other side, that is supposed to be an earthquake signature, anyway. This is the headline image from a recent news release and an upcoming publication on how the solar polar magnetic fields of the sun trigger the largest earthquakes on our planet, magnitude 8 and above. The paper, the manuscript, Kong Pop contributed to that as well, and because I am not a statistician and nobody would take my statistics very seriously, I got the statistics department from the Ohio State University to do this with me, led by Dr. Holloman there. Anyway, what this is a specific set of magnetic fields on the sun. When Kong Pop was talking, you could see the bright loops that were connecting the sunspots, and those are called umbral magnetic fields. You go a layer up, and there are these fields that we'll see in a little bit called coronal fields, and those arch a little bit higher and a little bit farther across the sun. Well, what we're going to talk about are solar polar magnetic fields. They come out the poles of the sun, the north and the south. Now, there have been many attempts throughout history to use elements of the sun to try to predict earthquakes or try to show that there's a correlation. And as we have seen with many single instances, this can be done very well. Very, very well. But in other times, it doesn't work so well. So for example, if you were to use sunspots, you could go through a year, maybe 2 years, and be genuinely convinced that this was a dead, perfectly accurate system. And then the very next year, you look and it hasn't gone away totally, but you're very much wondering where that perfect correlation went. Same thing happens with solar flares. You know, people have tried this with sunspot numbers for decades. They've tried it with solar flares as well, and they get pretty much the same thing. Sometimes these correlations make you drop your jaw, and then other times, usually right about the time you tell somebody to go look at this stuff, that's when it stops working so well for a little period of time, and then it comes back and you're wondering what happened. Then, as our ability to watch the sun got better and better, people started using the CMEs, the coronal mass ejection shock waves. Again, we have seen this one a little bit better. Very, very correlated, and it's not just these CMEs that are fired at Earth either. They can be fired in any direction from the sun, but when they get to Earth's distance away from the sun, these tend to be very highly correlated. Then again, of course, over the past week, we had a ton of sunspots, north and south. We had a flurry of M-class solar flares. We had a flurry of coronal mass ejections and geomagnetic storms and high-energy proton flux and electron surges. In fact, if you looked at some of the magnetograms, it looked like one of these coronal mass ejections that hit our planet last week temporarily, for about 2.5 hours, flipped the polarity of our magnetic field. That would be the GOES magnetometer. But again, no big quakes. We had literally sunspots, flares, and big CMEs hitting Earth with the geomagnetic storms, and yet we didn't have these big quakes. Well, why is it that sometimes we have these things going on and sometimes we don't? Why do these correlations appear to be perfect sometimes? Another one that they look at often is geomagnetic activity. I mentioned that with the storms, and Kong Pop did as well. People have tried sunspots, they've tried flares, they've tried CMEs, they've tried geomagnetic activity. Isolated, all by themselves, not looking at the biggest picture, not bringing everything in, but trying to isolate earthquakes against one other thing. Well, the problem with these so far has been that either their N is too small, and that means the size of their study. Either they're looking over just a few short years' time, or they're looking over one solar cycle, which probably isn't going to be enough, at least to convince me or most solar scientists that this thing works. Or sometimes they suffer from there being a lack of statistical analysis. They're saying, look, this happened, this happened, this happened, this happened. But what you're missing is all the other things in this list or in this list that don't match up to something in the other list. You see what I'm saying? Or the other thing they suffer from is there's no way to test these things, or there's not even a hypothesis about what the mechanism for this seismic trigger would be. Well, this is why as I come back to the polar magnetic fields of the sun, this is why I wanted to sort of put a lot of this together. I didn't want my N number to be too small. We wanted to use as much data as possible. Wanted to have statistics, because just showing this doesn't really work very well. So I got Ohio State statisticians to do the work on the polar fields for us. Still working on how to test magnetic fields of this size, but we are getting closer to a mechanism of how this might work, and that is actually thanks to Dr. Yen. He has actually proposed the mechanism for how these polar magnetic fields on the sun are triggering the earthquakes, and of all of the proposed mechanisms so far, Dr. Yen's is the best, and I'll mention that in just a moment. Anyway, what you're seeing here is a very, very simplistic view of the polar magnetic fields of the sun. Some of them indeed look exactly like this, but not all of them. The ones very, very close to the sun look like this, and the ones that stretch out past Pluto look like that. But there's ones in the middle that come off of the polar coronal hole and ride the heliospheric current sheet. This is the current sheet that Earth dives up and down through as it's orbiting the sun. The Earth is passing up and down through this current sheet. This is what we see in the solar wind called a solar sector boundary crossing. Now, you can see how these might be interacting with Earth just like a solar flare or a coronal mass ejection. I mean, we're talking about magnetic fields that wrap out of the poles of the sun, and they start right there at its edge, and they go out past Pluto. Some of those ride the current sheet potentially right to Earth itself. Keep that in mind. Let's take a look at what some of the trends are in the solar polar fields. This is one way to look at what I call the polar field cycle, and it is on the exact same cycle as the sunspot cycle of the sun. However, there's something a little different about it we'll get to in a moment. So we're starting here, and you can see in the very first image up top on the left, we have the blue southern positive magnetic fields of the sun, a little bit bolder. You can see the color better than you can see the red up on the top. There's about a 1-year oscillation between which poles are stronger on the sun. So go 6 months later to the image on the top right, you can see the northern fields, the red negative fields, they're bolder, they're stronger now than the positive blue southern fields. Well, after it does that for about 11 years, north, south, taking turns being stronger. they reverse. And you can see down on the bottom that blue and red have switched places, top and bottom on the sun, but they're still following the same pattern. The north is stronger, then the south is stronger. And this is what it ends up looking like. We end up having this thing that really follows the solar cycle, except we have a lot of things to be looking at. Now, one thing I want to mention about a different way of looking at the solar cycle. The published literature, starting back in the 50s and winding up just in the last few years, suggests that the shape of the heliospheric current sheet, the pressure of the solar wind, the number of sunspots and the position of the sunspots on the sun, the flare magnitude and the occurrence, how many flares there are, the frequency, all of these things, even when the cycle flips, it's all due to the polar magnetic fields. And as you'll notice, as these fields are flipping across the baseline, sort of like this, that the time when the fields reverse, that's when the magnetism of the poles at the sun is their weakest. But it's the time when the other magnetic fields of the sun are strong. That's when you get the sunspots, when the fields are reversing. It's when you get the powerful flares and the CMEs. You go to the areas here where the lines extend away from the central baseline, that's solar sunspot minimum, but it's the powerful polar maximum of the sun. And given the fact that all of space weather that we know of is dictated by what these polar fields are doing, maybe we should start to think about the solar system a different way. I mean, just picture this. You've got north-south aligned fields. And then as they flip, they've obviously got to come down through lower and lower latitudes, cross the equator, and then go back to the other pole. What do we see the sunspots do? We see the sunspots start at higher latitude, creep towards the equator, and then flip over. We see this with coronal holes as well. So, what is it about what we're seeing here that triggers large earthquakes? And by the way, you can also see that 1 year oscillation up and down, in addition to the longer 11-year polar field cycle. And that green line in the middle is actually the average of the fields. And so, what is it that is actually creating the earthquake? And I will go back for a moment. The analysis was simple. Most of the times in statistics these days, it's not simple. But the quote from Dr. Holloman at Ohio State University was that this is just plain simple. There is no complex factors. There's no complex math. And after I say this, you're going to say to yourself, those are the factors I would have picked if I had to do this analysis. The peaks in magnetic force of one of these poles. Now, don't just look at the top, you have to look at the bottom as well, because the baseline you see is in the middle. So something down at the bottom is really strongly magnetic, just magnetic in the negative. So when you have a powerful magnetic force of one of these poles, those are the times that we're most likely to get the large earthquakes. Or when you have one of these poles reversing polarity, that is when you have a chance to have these large earthquakes, and positive, negative, negative, positive. And the third factor is when the green line does it. The overall polarity of the magnetic fields of the sun changes between positive and negative. So we have the reversals in force, and then we have the peaks in force. That's it. Nothing else. We wanted to start very, very simply. I wanted to actually isolate half of the days as being more significant and half of the days being less significant, sort of turning it into a coin flip. Because you see, if you could identify 50% of the days within a given period as being significant for earthquakes, you'd be expected to get about 50% of the earthquakes, the large earthquakes within that period. But if you got 60 or 70 or 80 or 90% of those earthquakes within that period, within only a 50% window, someone might say, hey, your choice of that window, there might be something there. Turns out there aren't enough significant points along this timeline to create a 50-50 split and turn it into a coin flip. We identified 41% of the days between the mid-1970s up to 2014. We're talking more than 35,000 days. And so that's a big N number, by the way. And we're talking about 41% of those days. And we got almost 80% of the magnitude 8 earthquakes. Now you start going down to 6 magnitude, 4 magnitude, it doesn't work so well. Turns out this only works with the largest earthquakes on the planet. For those who are more statistically minded, the p-value on that was 0.0000015. But you see, the polar magnetic fields, these are really only helpful for a retrospective analysis of these large earthquakes. The polar magnetic field data is on a 3 to 6 week delay from Stanford's Wilcox Solar Observatory for reasons I don't fully understand. But so you can't really look at it and say, oh, this could be a time, because by the time the earthquake has happened, the most recent data you can see is just a couple of weeks old. I mean, it's already a couple of weeks old. However, there are things we can learn about this. You remember earlier I mentioned that when we are in sunspot minimum, the polar magnetic fields are straight up and down, and they're strong. But when we go to reverse polarity on the sun and we approach sunspot maximum, the sunspots and the coronal holes begin to leave the poles and come down towards the equator, eventually flipping. You guys might remember this. It was a different color when Kong Pop showed it. This is the southern coronal hole that was present during the Japan earthquake. This was just as this field was starting to flip. Now, the reason you don't see many coronal holes around the equator of the sun during solar minimum is because they're hiding from us. They're hiding at the north and the south. In fact, there are permanent coronal holes at the north and south poles of the sun. This is where the polar magnetic fields stream out away into space rather than looping back down to the surface of the sun. And what do we see in coronal holes? Unlike sunspot magnetic fields that loop back down to the surface of the sun, these coronal holes have magnetic fields that also stream out into space towards the planets. In fact, you can track the magnetic connections of the planets to the star. This is at a free online application called ISWA, the Integrated Space Weather Application. It's run by NASA. And you can see that the planets are only ever connected to the sun at these coronal holes. They are never connected elsewhere. So, here we have the same type of streaming out magnetic fields that we saw coming out of the poles of the sun before and riding along the current sheet. We see those same fields extending out of coronal holes, and we know for a fact that they connect directly to the planets. Well, the polar fields are nice for this retrospective analysis of major quakes, but what if you want to predict them? What if you want to be looking at these things and really being able to predict them a few days in advance? Well, coronal holes are a good place to start. There are a couple other ones that Kong Pop mentioned, and which I'll talk about in a moment, but as far as I've found, the ebb and flow of 6 magnitude earthquakes on this planet, which is generally considered the baseline for a significant earthquake, the ebb and flow of that appears to be dependent on coronal holes primarily. Now, what do I mean by the ebb and flow? According to the USGS, and indeed if you look at the data, this bears out, over the longer time scales you will have approximately 3 6 magnitude earthquakes every week. However, it is very rare to see a 7-day period with 3 6 magnitude earthquakes. You see none, or you see 1 most times, or you see 5, 6, 7, 8, or they've jumped up into 7 magnitude or 8 magnitude range. It is the ebb and flow of that, which on the long term comes out to 3 a week, but on that short-term variation, it's based on these coronal holes. This is what we do every day. One of the things we do every day in the news. And it has proved very, very fruitful. Just a couple other examples like this. Like I said, this is the one that was present during the Japan earthquake. This was 13 months later to the day, the first time we have ever seen 2 8 magnitude earthquakes strike in the same day. They struck the same location, Sumatra, April 11th, 2012. The very next 8 magnitude earthquake was in February 2013. This was the coronal hole situation then. This was the coronal hole situation later that year in late May, when an 8.3 struck very, very deep under Russia. We don't have a ton of good examples with those great magnitude earthquakes because the Solar Dynamics Observatory was just launched in 2010. And you can use SOHO and what's known as the GOES Solar X-ray Imager to go back before that, but there's really no substitute for what this new satellite has taught us. And every 8 magnitude earthquake since its launch has had an Earth-facing coronal hole. More than 90% of the 6 magnitude earthquakes and above have had an Earth-facing coronal hole. Why would this be the case? Well, it could be that those interplanetary magnetic fields that are put out by these coronal holes, the ones to which often the planets are connected, that could be one way this works. Or it could have something to do with what a coronal hole is and how it presents itself to the inner heliosphere. What you're seeing here is, I took this straight from NASA's website. This is what it looks like, a side view of a coronal hole. And these are supposed to be Alfvén waves emanating from the coronal hole. And without getting too technical or complex, it is generally understood that the Alfvén waves emanating from the centers of coronal holes are far more efficient at transferring solar energy to the planets than are the surrounding regions of the sun. So there's another option for how these coronal holes might trigger earthquakes. There's a third one too, and this one's kind of my favorite. You know, the sun is a giant sphere magnet. The Earth is a giant sphere magnet. These coronal holes are always polarized. They're either powerfully positive or powerfully negative. So we have this central sphere magnet, and we're living on another sphere magnet going around it. And a coronal hole facing Earth is essentially taking a strong, powerful magnet and just pointing it right at the Earth and then taking it away. Pointing it right at the Earth when it faces Earth and then taking it away. When you start to think about the sun and space weather in these non-traditional ways, your mind just can't help but race. Because you start to immediately get an understanding for how the Earth and sun could be interacting so well over such a distance. Of course, the other thing we look for to judge coronal holes on a day-to-day basis is the power of them. We can actually judge how powerful a coronal hole is. And we do this by gauging the solar wind coming out of a coronal hole. So the black lines that you see coming from the top left and connecting to the colored areas, that is known as Earth's magnetic connectivity. During the time I pulled this image from ISWA, the Integrated Space Weather Application from NASA, these were the coronal holes on Earth in color. And you can see over on the right side the speed of the solar wind coming out of them. Well, it's just fairly logical. If you've got one coronal hole blasting 700 kilometers per second wind and another one that's only blasting 500 kilometers per second wind, which coronal hole is stronger? It's quite clear. Now, I mentioned these earlier, these coronal magnetic fields. These are something else we use to judge coronal holes. By the way, everything I'm talking about right now is how do we judge whether or not a coronal hole is going to be really significant for seismicity? Well, first it's got to be facing Earth, but we also like to look at the size. We also like to know if it's transequatorial. What I mean by that is, does it cross the equator of the sun? That seems to matter. We like to look at the speed of the solar wind, like we saw there, but we also like to look here. This is the final factor that we use in determining whether or not a coronal hole is going to trigger seismicity. And it was not until we started including this factor that we hit that 90% mark on the 6 magnitude earthquakes. We were right around 80%. If I'm being honest, it was 79 point something before this. Not bad, but still, this is where you look. And what you have here is these coronal magnetic fields can sort of act to block the effect of a coronal hole. And so we will oftentimes see a coronal hole on the sun, and you come and you look at the coronal magnetic fields, and it's looking like it's getting pinched in, or it's crowded, or it doesn't have a nice wide opening to the solar system. So this first one right there, you can see an example of both extremes. The northern positive green coronal hole is vastly open to the solar system. The Earth-facing portion of the southern red negative coronal hole is entirely pinched and blocked by coronal magnetic fields. Now, pretty much do this day in and day out. Very, very simple. These things change. And interestingly enough, I don't have this slide here, but if you were to look at sunspot minimum, there would not be any of this undulation. None of it at all. It would just look like it wrapped around the sun like this. And why is that? Because there's nothing going on here. The coronal fields own it. There's no sunspots. The polar fields are all up and down at solar minimum, remember. And it's not until those reverse that we see these coronal magnetic fields start undulating, and the coronal holes leave the poles. The sunspots start migrating towards the equator and coming in full force. And by the way, given the fact that the coronal holes, what they actually do is they literally leave the poles and do this, what we're seeing with coronal holes, these are actually the polar magnetic fields, and we have just been mislabeling them for as long as we've known about coronal holes. These are literally the exact same polar fields that we looked at before. It's just this is them in the process of reversing. Fascinating stuff. Here's another example, just so you can see. We have a red negative coronal hole departing. It is transequatorial because it's crossing the equator, and you can see, and this is where some of the 3 to 4 day warnings about earthquakes come. You can see over on the other side that in a couple of days, as the sun turns, that green coronal hole, the positive one, will be facing Earth. Now, of course, what is it that we're really trying to do here? As Kong Pop said, we're trying to predict these natural disasters. And I sort of started with a question that I never really came back to, and that was a bit by design. Why is it that sometimes these things look like they are the absolute trigger of earthquakes and volcanoes and storms, and yet other times you'll say, what happened here? This was working so well. In fact, despite everything that we've done with the polar magnetic fields, that goes as well, because we had 41% of 35,000 days. There's going to be some days we identified as significant that there were no massive earthquakes. And we only got 79% of the massive earthquakes in that 40%. So there were some massive earthquakes, and the polar fields were not significant at that time. So what is it that we're doing here? We shouldn't really be ignoring these periods where you can see it so clearly. This isn't a coincidence. This is more of dependence, cause and effect type of thing. But you also can't ignore these periods where it doesn't seem to work as well. What you have to do is you have to bring everything together. You can't just look at coronal holes. You can't just look at the polar magnetic fields. You can't just look at CMEs. My God, we got hit with 5 CMEs in the last week, and it's been one of the lower times of seismicity that I can remember. So what is it? It's looking at all of these things together and including the planets, which I did not talk about, but which are very, very significant. And so what you have here is, this is how we create earthquake watches every day. Like I said, that is a part of our daily news. We look at space weather, earth weather, what happened seismically, and also predicting what's going to be happening seismically. The number one factor are these polar magnetic fields, and I'm sort of lumping them in there with the coronal holes because, as I said, I believe these are literally the exact same fields. They're just in the process of flipping. And so the primary earthquake factor is our coronal holes. Second, and a very, very close second, is the geometry of the planets. And as Kong Pop was saying, because we have this resonant connection, we have this interaction with all the spheres in the system, Earth does not even need to be involved. You might remember that. Kong Pop just mentioned that a few minutes ago. The Earth does not need to be involved in these planetary alignments. Because if the sun is involved, if the sun is shaking, we're going to couple with the sun and we're going to shake as well. And of course, third is just general space weather energy as well. Things like the CME shock waves, things like the large solar flares, sunspots. Something that's actually proven itself over the past couple of months to be a pretty good factor are those solar sector boundary crossings I mentioned when Earth passes up and down through that heliospheric current sheet. But those are generally considered the third factor we use. But indeed, it is only when we see these things coming together that we tend not to miss big earthquakes, and that we tend not to call out periods of significant earthquake watches and have there be no tremors. So, the question at the start of this talk was, does the sun trigger large earthquakes? And if you think about it the way Kong Pop was describing it, you might want to say, well, yes, the sun is triggering earthquakes, but there's a lot of other things involved as well. Just like I might say, yes, the coronal hole is a significant earthquake factor, but there's other things involved as well, like the planets and coronal mass ejections, other things of that nature. Well, the answer is fairly definitive. It's a yes. There will always be people who will push back against stuff like this, against the electric universe as theories as a whole, anything that challenges the mainstream, really. However, we've now got professional statisticians showing us that this stuff is real. If that's not your cup of joe, come over to the Suspicious Observers and do this day in and day out. And I don't mean watch me do this day in and day out. I mean you do this day in and day out. There are hundreds of people all over the world emailing me their earthquake predictions every week, and they're correct. I promise, if you watch the news every day for 30 straight days, you'll predict your first earthquake. And you'll be right. You will. One last thing I want to mention is the mechanism for how some of these things could be working. And I mentioned that there have been a number of mechanisms proposed, and that I was most in favor of Kong Pop's explanation. The idea is piezoelectric, and I'm sorry if I botched that pronunciation. But essentially, this is the buildup of energy beneath the ground and the triggering of that energy. You know, when a coronal mass ejection sweeps by and hits Earth, it's not like the Earth wobbles. There's an integration of this energy. As Kong Pop said, we have noticed things like changes in the atmosphere in terms of ions before earthquakes. We've noticed quite a bit of that. It's what's coming to be known as lithosphere, atmosphere, ionospheric coupling. A man named Sergei Pulinets has basically dedicated the last decade of his life to studying this and this alone. Essentially, what we have is literally electric coupling mechanisms from the edge of space down to the ground. And what Kong Pop was mentioning earlier, we have seen electron content variations. How much energy is in the atmosphere before the earthquake? We have seen critical frequency variations before these earthquakes, which is the critical frequency is the maximum power wave that you could skip off the ionosphere. We've seen that change as well, and that is wholly a factor of how much energy is there to begin with. We have seen evidence of this energy above and below that layer as well. We have seen evidence of electric currents, static, going through the ground at up to 1 million amperes during these seismic events. And we have seen local and global scale magnetic fluctuations before some of these events. And the only real way for this to be possible is if you've got an external trigger. You don't have something beneath the ground. Maybe you have it releasing some positive ions and changing the atmosphere a bit. You don't have it vastly changing the ionosphere. You don't have it perturbing magnetic fields. You don't have it surging electric current through the ground. What we're talking here is something external. And while, you never want to express certainty, absolute certainty, the p-value on the study, the day in and day out, and the logic of just how well this works, combined with our observations of pre-earthquake signals, not really having a good explanation if you're looking internally to the Earth. Combine all these things together, and you have to say that you're pretty confident that the sun does trigger large earthquakes. Thank you guys for listening.